How are we doing? Yes, I think we are 1:30 now, so I better get moving. So good afternoon, everybody. We've got two presentations this afternoon from two more OU students, one of whom has graduated and the other one who is yet to graduate, and in fact is only just really beginning to get moving on his project. But first of all, I'm going to share a few thoughts. And even before I do that, I'm going to go through my presentation, which is just a rather different presentation from the first two you've seen. As you can see, I'm going to be capturing some of the recent stats from the catalogue of exoplanets at exoplanet.eu. And I want to show you these because I think they do tell an interesting story. First of all, how many exoplanets have we had confirmed? Here they are. This might be a surprising number to you. 7,414 have been confirmed. They're in 5,086 stellar systems, and of those stellar systems, 1,035 are multi-planet systems. What does that tell us? It tells us that 2,328 of the 7,414 planets are distributed amongst 1,035 multi-planet systems. And that tells us a little bit about the scope for using TTVs to infer the presence of additional planets and systems which have not been confirmed so far, may not have been detected so far, and in fact may not even be transiting exoplanets. If we extend that number to planets that have been either confirmed or are still in candidate status, not confirmed yet, then that number goes up to 9,790, which means that sometime this year we're going to get to 1,000 exoplanets, which will be quite a remarkable achievement when you consider that we started off in 1995 or so with the first ones to be discovered. 1992 it was. And those 9,790 planets are distributed amongst 6,968 stellar systems, of which 1,267 are multi-planet. So what is the percentage? If you have an exoplanet at random, you choose one of these, say 9,790 exoplanets, what is the chance that it's in a multi-planet system? Well, the answer is 29%. And if you just limited yourself to confirmed exoplanets, it would be 31%. So it looks like, in round numbers, about 30% of planets that we have either confirmed or are candidates so far are already known to be in multi-planet systems. Right, so that's useful when we're thinking about using TTVs to discover new objects. Let's just look very briefly at the third category on my slide here, which is confirmed and detected by TTV analysis. Now that's a small number, 34 planets, of which 30 are in stellar systems. Now this is interesting. I put down there that 4 of them must be in multi-TTV detected planet systems, but I'm having second thoughts about that statement because I haven't been able to check it with exoplanet.eu because as of the last day or so, their site has been down. I haven't been able to get on the site. I know Paul was there midweek, but since then something seems to have happened. But it may be just that I've caught it when it was due for a downtime. I don't think that last statement is true because we've got to understand more. And I did send a question to the Exoplanet EU people about whether they can split the analysis up to planets which are known to be celestial bodies, but also, of course, perturbations due to ploughing through stellar material and all the other things that Roger mentioned first thing this morning. So I think there's a little bit more to do there, but the number of TTV produced planets is quite small. And, loosely speaking, given the numbers I've just given you for the confirmed and candidate planets, it seems to me that there is a considerable potential for amateurs, as well as the professionals, of course, to see whether they can, in fact, find additional detections. That's a loose argument, but I hope that begins to help a little bit to assess it. And in case you're wondering, the definition of an exoplanet is nothing more than being, it can be confirmed when a professional, or at least a contributor to a peer-reviewed journal, says it is. There is no formal, as far as I can see, definition of when an exoplanet can become confirmed, other than it appears in a rigorously refereed journal. Okay, so another presentation that we can give is the following. Is that being covered up by my, yeah, I'll put that down there. Oops, now it goes over there. Oh dear, where does it go? Can I reduce that in size somewhere? Maybe not. Here we are. Let's do that. Oop, comes back again. Put it off to one side. It refuses to go away. Okay, so look, here is a map of Earth-sized planets between 0.5 Earth radii and 1.5 Earth radii within 10,000 parsecs of the Sun and the Earth. And you can see that's the current distribution as of a few days ago. What is the big clump of planets? That is, of course, the Kepler field of view. And what that tells us, of course, is that there is a hell of a lot more Earth-sized planets that we're going to be discovering in this region of space between those two ranges, between 0 and 10,000 parsecs, and also at any right ascension that you care to think about. If we had more Kepler-type telescopes with a long stare into a particular direction, then we would expect to see a lot more Earth-sized planets. Simple conclusion. And we can extend that particular graph from Exoplanet EU to include, for instance, if my next picture goes well. No, it's not going to go now. Why is that? Is that because I'm covering this up, I wonder? Try that. No, dings again. How do I push this on? Ah, there we are. It's come now. It took a while to change. I don't know why that is. So here we have the same picture, same type of diagram. And this thing is jumping around the screen here. Super Earths. 1.5 Earth radii to 2 Earth radii. And I can quickly compare the two diagrams. No, I can't. It doesn't seem to want to do it. But take it from me, there are a lot more super Earths than there are Earths on the previous diagram. And again, of course, Kepler was able to find a good bunch of them there, down there. Okay, so there's two examples of what you can get from Exoplanet EU in terms of where we've got to with exoplanet detection and confirmation. And again, I have this problem of not being able to push my slides on, unless I use this thing down the bottom here. Maybe that works. Oh, that's better. Okay, so my computer refuses to allow me to use the up and down arrows, but I can use the arrows embedded in this. Now, here's another diagram which I've taken from the Open University's bespoke book for our S384 students. These are our final year BSc undergraduate students specializing in exoplanets and stars. We call it astrophysics, and astrophysics these days is very much as much about exoplanets as it is all the other classical elements of astrophysics. This is from page 34 of the course book. It's about 2 years old, and it shows the distribution of exoplanets by mass and orbital period as the axes, you can see there. And you can very clearly see that different detection and confirmation methods listed at the top clump together in certain parts of the diagram, in certain parts of the orbital mass two-dimensional space. And so this is a very important aspect for anybody who wants to be thinking about doing amateur research in TTVs. And the reason I say that is because, going to the next slide, we need to look at selection effects. And the first, what I'm going to do is go through several of these, probably just 3 or 4. These are all selection effects which are subject to some modeling, and the modeling is well explained in our exoplanets course book. So if we take transit probability as a starting point, what we're talking about here is what fraction of exoplanets around stars are actually going to be transiting across their host star. Well, you can do the geometrical analysis and you come up with a very simple equation. And there it is. The geometric probability of transit boils down to the radius of the star over the semi-major axis. Actually, the A there is the semi-major axis of the sum of the semi-major axis of the star plus the semi-major axis of the planet around their common center of gravity. But it's proportional to the semi-major axis of the planet itself around the star in a different reference frame. So it boils down to simply the ratio of the radius of the star to semi-major axis. It's not that surprising, really, but what it says is that if you want to have a good probability of seeing a transit, a geometric probability, then you need a fairly large star, please, and a small semi-major axis. And I guess if you did a little sketch of a typical transit, you could quickly see that that makes a lot of sense. And that explains partly the previous diagram where we see transits, the transit method specializing in fairly high mass planets and fairly short periods. And that can translate into the same, you re-express that in terms of the transit probability. Okay, so that's one. The next one is the radial velocity method. So we look at the reflex orbit of a star with planets going around it, and we measure the amplitude of that radial velocity using spectroscopy. And we can come up with a geometric analysis of the selection effect on these on this radial velocity method. And it comes out to be this. This will be very familiar to Paul and other students. It comes up with this selection effect, which you can see has the semi-major axis on the bottom. So the smaller the semi-major axis, the better. It says that the mass of the planet is a good thing to have if you want to find a measurable amplitude of the stellar radial velocity curve. And it's also got something to do with the inclination of the orbit as well. So you can see now as we go through these, I'll go through the next one quickly. This one here is the the detectability of a transit. That's a very familiar one, of course. It's simply the radius of the star squared over the radius of the planet squared over the radius of the star squared. The bigger that ratio, the more likely it is that you're going to be able to see a dip in the light curve as the planet transforms across the star. And we can also now, with Gaia data release 3 and further data releases coming, look at astrometric detection. The signal is the Greek letter. What is that letter? Phi, probably phi, is going to have that sort of sensitivity. And if you want to be measuring using astrometry to find exoplanets, then you better be beware of that selection effect to do with the period of the orbit, the mass of the planet, the mass of the star, and the distance of the system from the observer. So there's some examples of selection effects. And if this pesky screen in front of me would go away, I'll put it away now. There we are. I'm now asking the question, what about transit timing variations? Can we come up with a set of selection effects which we need to take care of in both directions of the process of inferring the presence of other bodies in a stellar system, going from TTV sequences to inferring the presence of exoplanets, other exoplanets, or going back the other way, modeling particular exoplanet, unknown exoplanet orbits and masses, and maybe eccentricities, and coming back to finding patterns of exoplanet, patterns of TTVs that we would like to look for. I'm not saying both of those are equally important, but just to raise the issue of what should we take account of when planning our attack on using TTVs to find other bodies in stellar systems. Right, I think that is... one more. So this is just a graph that I produced the other day, just yesterday, I think it was. It's gone already, disappeared. Back again. So here we have, there's our 34 exoplanets discovered by TTV analysis. You can see that the majority of them come from Kepler, 2 from WASP, 3 from test objects of interest, and 4 others which I haven't been able to trace. And it's a fairly regular drumbeat of new discoveries or confirmations of TTVs. And I'm not exactly sure what the 2014 peak would be, but it may be a concerted attempt to analyze Kepler data. And I think that what that tells me is that maybe the field is ripe for a group such as ours to see whether amateurs with performant computers can start the process of increasing numbers of exoplanets discovered by TTV analysis. Right, there we are. That's it. We can take some questions at the end. I'll go back to stop sharing so that somebody else can come on in. What units are used in probability equation? It's a probability. It's one number over another. Any number between 0 and 1. 1 being it happens all the time, and 0, it never happens.
Rodney, what I meant was, what do you measure the radius of the star in and the orbit in?
Oh, well, it doesn't really matter. It can be kilometers or... Yeah, kilometers. Let's be scientific.
So both in kilometers. Okay.
Oh, yes. They're both going to be in the same units. Otherwise, that would be cheating. Yeah. Right. Okay, so now on to the afternoon speakers. I'm very fortunate to have 2 enthusiastic students who have reacted in short timescales to present their ideas and what they've been doing. Daniel's up first. Daniel is also a graduate from the MSc conveyor belt, and he's been looking at a question of interest to the OU, which is what can our two telescopes in Tenerife contribute to various space missions? And one of the issues that we've come across, Daniel came across very early on in his 9 months as a student, is the problem that is faced by the Plato mission by looking for Earth-sized planets around noisy adolescent M-type stars, which they are noisy because they are spotty. They have lots of star spots, and they're also noisy because they flare up at the slightest notice, and they will definitely be upsetting transit observations. So Daniel, in his 20 minutes or so that we've allotted for him, perhaps there'll be some questions as well, is going to tell us about his approach to seeing whether our 50 centimeter class telescopes, in fact, Pirate is a 60 centimeter telescope, can have any role to play in helping a mission like Ariel, a multi-billion-dollar program, launching in Christmas 2026, whether we can hope with relatively small telescopes to contribute in some way to the search for Earth-sized planets around M-type stars. Daniel, you should be able to get your screen up. We can't hear you either at the moment, but
Can you hear me?
Yeah, we can now. Okay,
Good,
I'm going to
good.
go away because I'm still sharing my screen, aren't I? No, I'm not.
No, I
I
can share
can close
mine.
myself down. Video goes away. That's it.
Uh,
Yep, that's good.
yeah. Hi, everyone. My name is Daniel Barbos. I have recently graduated um, from the Open University with degree in space science and technology, a master's degree. And I would like to share with you some of my the idea behind my master's thesis and um, what question I was trying to answer and how far I got with it. I'll give you a little spoiler, not too far, but the idea is still worth exploring. So let's um, get to it. So basically, the question is: can Earth-based telescopes can help space-based telescopes in increasing the quality of the data? Basically, by the means of post processing. Let's see, there you go. So the purpose of the study is to address how Earth-based telescopes and amateur astronomers community could contribute to reducing noise in exoplanet transit observations. Why does this matter? Space telescopes have a limited observation time. As we know, there are quite a lot of stars. I mean, the Plato catalog, I think at the moment is still around 2.6 million potential targets. So quite a lot of stars, but little time, little observation time available for each telescope. So how can we improve? How can we use that time effectively and efficiently and dedicate space-based observations to a transit only, but then use Earth-based telescopes to assist those observations. Let's move to the one. So what I will be covering in this session is the problem of noise in exoplanet observations. I would like to talk a little bit about the Lomskargel periodogram, which is a key tool. It's also what I've been using in my study. And a brief summary of my research methodology, some of my key findings, and how can amateur astronomers contribute to scientific experiments. So let's move on. Yeah, so the problem of noise in space-based observations. Basically, the exoplanets transit, the characterization of exoplanets in terms of radius, for example, is dependent on good quality data. Small dips in brightness can indicate planetary crossings, but intrinsic stellar variability can mimic or obscure these signals. So what kind of noise can affect the observation? So stellar activity, basically spots, flares, pulsations, they create fluctuation in brightness, which means highly volatile data. There are other types of noise to be accounted for, such as instrumental noise, atmospheric interference, but the focus of this study was mainly on periodic intrinsic stellar variability. And periodic because it's easy to predict. So I'll talk about that more in shortly. So the case study is based on Plato and Ariel missions. Now, because they're both the next missions to study exoplanets, and Ariel is already benefiting from the amateur astronomer community with doing real science and contributing to the science to the observation data. I try to combine the two and basically find common targets, and I will explain why shortly. Let's move to. So yeah, how can that happen basically? As we know, like I previously mentioned, short time for space observations, but on Earth we have the luxury of time, and we have the luxury of access to multiple telescopes. But not even though they're not as sophisticated or as are not as precise of the space-based telescopes, there's still potential for them to contribute to science. Now, by monitoring stellar activity during out of transit periods for prolonged time, there is a potential to model the intrinsic stellar variability and use that data to then apply that model, the inverse of that model to space-based data and reduce the noise for more accurate results. Or at least that's the idea behind the study. The role of amateur astronomers in this is that many amateur astronomers have access to high-quality telescopes, possibly as good as Pirate, the one that belongs to the Open University. And it's been proven that amateur astronomers can contribute to scientific observations through the exoclock framework. Now the question is, how can we expand on that? Is it possible for the exoclock framework to expand, or to use that as a basis and create new tools for using Earth-based observations for space data? So now let's talk a bit about LOMS cargo. As you can see in the top left graph, LOMS cargo is designed to deal with irregularly sampled data, which makes it suitable for astronomy, because in many occasions you don't have the luxury of observing something for days in a row without obviously dealing with the weather, dealing with night light cycles, and so on. So on the top left image, you can see an example of irregularly sampled data. Now, what Lomskargel can do differently than a simple fast Fourier transform is that it can deal with those gaps. It can handle those. And in the top right, you can see an example of data I've captured using Pirate, and by applying Lomskargel, I could see some spikes, some regularity there. On the bottom left image, you can see the difference between originally captured data and after applying the Lomskargel, the inverse Lomskargel on that data, how that reduced the overall flux, but kept its the data quality. So basically, it's reduced the standard deviation in principle. Moving on. So the research methodology is fairly simple. The first part of my thesis was to identify, basically to merge the Plato and the Exoclock catalogs, and I said I was going to talk a bit more why combining aerial. I'm using Exoclock and aerial interchangeably because Exoclock is focused on aerial targets, but the idea was, let's see if we can assist Plato, which is targeting Earth-size rocky planets. But at the same time, I wanted to use the Exoclock framework because it's such a good tool to for someone with little experience in astronomy. It gives you all the scheduling, it gives all the suitable planets for your telescope, observation time, and it gives you HOPS, which is the tool to process the data. So I wanted to make use of that to stay closer to the amateur, to the tools normally used by amateur astronomers, and see how far I can get with that. The next step was to use Pirate. Like Rodney mentioned earlier, Pirate is the OU owned, one of the OU owned telescopes in Tenerife. So once the target was selected, I've used Pirate to do some observations. Now I wanted to do both in orbit, in transit, and out of transit observations. In transit to have the actual transit data that I wanted to post-process. Out of transit to have something to determine the intrinsic noise, or stellar noise of my target star, and see how applying the inverse of that model whether that would improve or not my light curves. And out of transit, I also want to mention that the out of transit observations were done by using the filler request, which at the time seemed a really good idea. As you may see in the results, it wasn't such a good idea, but the reasoning behind it was, okay, let's use filler requests, which don't clash with others people observations, is easy access to observation time, and the gaps between those filler observations, the hope was that Lomskargel could fill them. Again, in my results section, you will see why that didn't quite work. So yeah, then the idea is to apply the Lomskargel periodogram on out of transit data, model that, and apply the inverse of it on the in-transit data, and check for improvement. Results and key observations. Now, merging out of transit data, here's some obstacles I faced. That trying to merging out of transit data observation, basically the filler requests, there were some issues due to different high differences in flux, in total flux, large gaps between observation times. There's a graph in the next slide that will display that better. However, I still made use of that observation of the data I had available to pick a single continuous observation, apply Lomskargel, and reprocess the data. So the light curve now, as you can see, it's not a full light curve; it's just a partial one. For some reason, these are the challenges in astronomy. I always missed the transit window. It was either too soon or too late. However, I got a partial transit in this case. I processed the data using ARPS, plotted the light curve. Then I took the processed data and applied the model created using Lomskargel, applied the inverse of the model, and reprocessed the data, replotted my light curve, as you can see in the image at the bottom. And while the light curve seems to have seems to be a bit more visible, increased. However, the standard deviation also increased, which sort of indicates towards a decline in the quality of data, which is why I was saying at the beginning, I didn't get too far with the data I had. However, the idea is still worth exploring. Let's move to the next slide. So, like here in the challenging and limitation. So basically, the gaps between filler requests, as you can see in the top graph, the little observation times compared to the large gaps, flux inconsistencies, because they were obviously taken at different times. I was going to say of day, but it was different times of night. It shows some challenges, which is why in the end I took a single observation to plot that noise and to use for my study. And you can see in the graph below as well a sudden drop in flux. Again, this could be due to the telescope turning from one side to the other. Sometimes I'm not sure, I don't know how to explain it. But basically, if you're looking at a portion of the sky, sometimes you're turning your telescope to the other side. So that's what I assume it might have happened here. Moving forward, so how can amateur astronomers contribute in space observations? Basically, we know that Exoclock has proven to be a successful way to allow the amateur astronomers community to contribute, and that's that would be a first step. Participate in Exoclock if you're not already, and monitor stars with high variability and see if there's a periodicity, anything periodical in that data. So maybe a less ambitious target, maybe not a rocky-sized Earth-sized planet, but a hot Jupiter would be ideal to start with, and perhaps the results will be a bit more promising. Conduct long duration out of transit observations, again for trying to characterize the noise, the intrinsic noise of these targets. Use Lambscargle. So I keep mentioning that I've used Lambscargle. Now, there are some great libraries in Python. I think it's part of the AstroPy library that's already available and quite fairly easy to apply. So also hops gives data in numerical format. So you obviously import your fits images in hops, but then once you've processed them, you have access to a CSV file that you can import in Python. So doing that, you can actually post-process data that's been that you only have the images of, and then improve collaboration with professional observations. Now, here I would like to emphasize that the way Exoclock has provided an easy to use framework to amateur astronomers, that is the goal. That's what would ease this collaboration. So in the idea of using Earth-based telescopes to reduce noise, to capture data that's then to be used for post-processing space observation data, I think it's crucial that the scientific community creates the tools and makes them available to the amateur astronomers community. Moving on. So next steps, what have I learned from all this is that better scheduling of outer transit observation is necessary. That using the filler request was not such a good idea due to large gaps and little time availability, little observations. So better scheduling for out of transit observation would make things would have a better impact. Improve target selection. Again, my target was quite an ambitious one, very small planet on a faraway system was not the best choice. So I would, if I were to do it again, I would choose a simpler target, something that's more obvious. And then moving forward, explore alternative noise reduction techniques beyond Lambscargle. So Lambscargle is not the only pattern recognition algorithm that's out there. It's in fact fairly simple. Well, I say simple. It's similar to fast Fourier transfer, except it's actually accounting for gaps between observation. But with machine learning and all the AI tools available nowadays, which is also quite accessible via Python libraries, I would explore more techniques in trying to find patterns in stellar variability, and increase amateur involvement in noise modeling for space observation. So as I said before, it's probably the scientific community's duty to offer the right tools. However, there are plenty of talented people out there with highly motivated, lots of interest in computer science, and because astronomy is starting to, well, it probably always has been, but it's more and more closer to data analysis, and computer science. So applying data analysis algorithms, even it might be that it could happen the other way around. That it will be the amateur astronomer community that will come up with better ways and better tools to explore this idea further. And in conclusion, yes, we know that ground-based telescopes can support space missions. Exoclock is a good example. Stellar variability modeling needs more refinement. Again, the this work, my work was strictly focused on Lambskargel. Exploring different tools would be a good way to move forward. Amateur astronomers can play a vital role in exoplanet science. Again, Exoclock, it's a good example. And next steps: improve target selection and observation strategy. Thank you.
Okay.
Stop sharing now.
Well done, Daniel. Bang on time. You haven't left any time for questions. I think what to do is to, if you can produce your screen sharing. I think the best thing to do is to have Ashok come on now, and then we can handle some questions all at once in about half an hour's time. So the next speaker, Ashok Kumar, is not a graduate of the Open University, but he will be by the end of the year, I think. So we're getting the impression that LOM and Scargill are rather important for the sort of things that we want to do. And Ashok, at very short notice, has produced a delightful presentation. He's going to share his screen with us, and he's going to using a Jupyter Notebook live. He's going to show us what it's all about. LOM Scargill, how does it work? What's it good for? And who knows what else he might be able to say in half an hour. So over to Ashok. Ashok, by the way, is 3 hours ahead of us. So he's in Bahrain. It's almost his tea time. Over to you.
Thank you, Rodney. Let me share my screen.
Yeah.
So is my screen visible and am I audible, Rodney?
Yes, that's good. I can see Google, and welcome to the BAA webinar. That's you.
Yeah, cool. Good afternoon, everyone. And I'm Ashok. So I live in Bahrain, and for my day job, I work as a software engineer in fintech. So I've been into software for a while now, and in the weekends mostly the OU stuff. Like I'm doing my masters with the Open University on space science and technology, and I'm gearing up for the final project for the masters, which Rodney is helping me with. The idea of my project for the masters is quite similar. I mean, around the same idea which Daniel, I think, has already explained. So the idea is to see whether the 50 centimeter class telescopes, Pirate and Coast, which are in Tenerife, can contribute to transit time variation measurements. Specifically, only for that, we are trying to find out various methods. We have many options that we want to iterate upon, and find whether we can use the ground-based telescopes to improve the TTV output overall, and help the aerial mission as well in the process. So one of the ideas, one of the primary ideas is to point both Pirate and Coast, two 50 centimeter class telescopes, at the same time on the same target when there is a transit happening. So it's called synchronized measurement, and we want to take the output from both Pirate and Coast and see if we can reduce the noise, like Daniel has already mentioned. And in that process, we're not so the target is not to measure the transit duration or the depth, but to find the appropriate center of transit. So center of transit is very important to look for transit time variation, right? Because the time between two transit midpoints is the actual period of the orbit of the planet, and when the deviation in the period happens, then that there is a room for additional perturbation or orbital decay. So getting the center of transit as accurate as possible is very crucial. So we are just gonna use Pirate encores to their maximum to see if it can contribute to TTV. So that's the project that is in works. Just in a very early stage just now. I cannot talk about that much because it's still in progress. But I think what we can spend next 15 minutes on is something going back to basics and play with the data. So the topic which I have collated is the curious astronomical cycles. So cycles are everywhere, right? So this quote came to my mind, and so life is a cycle of ends and starts, right? So looking around us, like everything is a cycle. It has a start and an end and a repetition. So when there is a cycle, then there is a period, there is a frequency. So first question that comes to my mind for our mind is like, what is the frequency in which the cycle happens, right? So this, I will take this in various levels. So bear with me if some information is redundant or very basic, but let me try to build upon from the scratch. So let's take level 1, which is just ideal signals. So in the plot, what we see is two sine curves, right? Like one has a higher frequency, the other has a relatively lower frequency. So the blue one is like in 0.1 seconds. So this is a 10 hertz sine curve, and this is 5 times that. So 50 hertz. So we have 10 and 50 hertz frequency, right? When this happens, for example, if we are getting these two signals, if we are measuring these two signals at the same time, I mean, we get an additive. It gets added together, and in the measurement, it will be added together, right? So when this gets added, so it will look something like this, right? So it's very difficult from the original signals. It's easy to, as human, it's easy to interpret the period and find the frequency as well. But when more than one signal combines, the human ability to decode the different frequencies is drastically reduced. But all the real world signals is a combination of multiple signals. So it's very important to have tools developed and mathematical formulas and methods to derive frequency and patterns out of a signal. So that is where this motivation. So Fourier, Joseph Fourier is a French mathematician, was developing Fourier series, so which led to Fourier transform. So Fourier transform is a way to transform this time domain signal into its frequency domain signal. So for the same signal, if we pass through the Fourier transform, so Fourier transform is widely used, more prevalent across everything you touch. So basically signal processing, engineering, and all aspects. So if I apply fast Fourier transform on the above data, so you get an output something like this, which corresponds to 10 hertz and 50 hertz. No surprise there, because it's so that is what the Fourier transform intends to do. Let's do one thing. Let's have another frequency. So I'm just doing some things just for fun. So I'm just trying to add one more signal, which is let's say 75 hertz. And if we do this, then we have a signal like this, and it's definitely out of our reach to find the frequency there. And applying there, it nicely picks out 75 as well. So Fourier transform works well for for the ideal signals. Let's go to level 2, which is the real world signals, right? Any real world signal comes with a noise. So this is the same similar 10 hertz and 50 hertz frequency, but with some kind of noise. So as humans, we are able to still relate to this curve and find the frequency. And if we run Fourier transform on this, we still get the same 3 signals. Sorry, I have to rerun this. We still get these 2 peaks, 10 and 50 hertz, but as you can see, there is a lot of the reflection of noise is there in the frequency domain as well, in the below the false alarm probability, which is, but the peaks are still very solid and clear. It's standing out. So let's increase the noise a little bit. Let's say, so if we do that, now the signal is completely absorbed by the noise, and the noise is taking precedence. Surprisingly, if we apply Fourier transform, still we can still find the frequencies, but you can see that the noise is increasing, right? So all good. Even with the level 2, with the real world signal and the noise, the Fourier transform works. Let's go to level 3, which is the non-continuous nature, right? Like for level 1 and 2, we are dealing with the ideal signals, but nothing is continuous in the real world, right? Like so any digital processing or any measurements is going to be discrete and not continuous. So let me introduce Dirac comb. This is a kind of signal similar to how we measure like consistent measurements happens in this pattern. This is called Dirac comb. So we have zeros and ones. So whenever there is a 1, there is a measurement, and the instrument goes to idle, and there is no measurement for some time, and again there is a measurement. So this pattern is called the Dirac comb, and so this is how even the telescope, we know that the telescope shutters opens and takes a measurement, goes idle for some time, and again it measures, right? So it's not always continuous, it's discontinuous. And so let's see how the Fourier transform behaves for the non-continuous signals. Let me try to plot this. Sorry. So we have the Dirac comb here, and let me add the signal back. So this is a signal, and this is the Dirac comb. So when we combine those two, so the actual signals will look like this. So we are trying to, the next step is we will be trying to find the frequency within this kind of mess. Let's try to apply Fourier transform on this. Okay, so we see some interesting patterns here. Let me rerun, sorry. Okay, so what I'm doing is I'm just applying Fourier transform on the Dirac comb itself, neglecting the frequency. So when we do that, it rightly picks out the frequency of the Dirac comb, which we call it as a window function. I'm going to apply on the total signal now. So when we do this, our original signal frequency was 100 hertz. So there is a spike on 100 hertz, but you see a larger spike on 300 hertz. This is directly because of the contribution from the window function. So this is a combination of window function power spectrum plus the actual original signal power spectrum. So that's the difference between the non-continuous and the continuous signals. Let me move forward. So the next level of complexity comes in when so the Dirac comb which we saw just now is a repetitive measurements at the same interval, right? But we know that astronomy measurements are not always uniform. So if we for example, let's take this output. You have a signal and the measurements are quite random. So here also the signal is 100 hertz and I'm sampling the number of samples are 20. So there are 20 readings here, and when we try to process the non-continuous or the non-uniform sample signal in Fourier transform, it fails because the actual frequency is 100 and we can see multiple peaks everywhere, which is kind of random. So this is where the Fourier breaks. So alternate I think Daniel has already touched upon Lomskargel. So this again extension of that. So Lomb in 1976 tried to propose a method for analyzing unevenly sampled time series data, and Scargill took upon that and improved the method, and which from then we were using the Lomskargel method for detecting the periodic signals in light curves. It's highly useful in the exoplanet detection, variable star analysis, and all the pulsar studies, and so on. So here we have the same data, same signal, random non-uniform sampling. When we apply Lomskargel on that, we see a peak clearly on 100. So the number of samples is 50. Even with, if I reduce the samples, right, let's say to 25 or something, the number of samples is reduced, but still we can see a prominent peak in 100. Let's see where it breaks. Even with just 10 samples, you can still see that it's picking out 100, but we can see the other areas growing. So this is an example of Lomskargel applied on a non-uniform signal. Let's take two interesting targets. So TOI 1181b is such a gas giant discovered in 2022 by transit method. So I just tried to pull the data for that from MAST archive. So it looks like this, right? So I just pulled 25 days of data for this exoplanet, and we can clearly see the transit happening, like almost 10 transits happening within 25 days. So 10 transit in 25 days is almost the period of around 2.5 days, right? So let's see how the machine approaches this. Let me rerun this. So when we apply Lomskargel on that, so we see the peak is on 2, like around 2.1 days. So that's a base period. So even if we reduce, right, like not apply on 25 or more than that, and let's say on half of the data, right, we just see only, let me reduce further, we just see 4 transits. Still just for 4 transits also, like we can see the peak prominently in 2.5. So sorry, not 2. I think around 2.1, which is, I think, which is the orbital period for 1181b, right? So it works to find the period for any exoplanet. If you have more than one transit, then applying this will easily give you the period, but that's still basic, right? if we look at another target TOI 2202b, so it has this planet has additional perturbers, like it is found to be in mean motion resonance with another planet, but not directly observed by transit, but inferred by the transit time variation. So this is one such planet. If we try to apply Lomskagel on this, we don't see we see the peak broadened, right? Like we see it still tries to find the period, but the period is no longer sharp. We see a broader base, so that is a good indication of TTV. But it's still hypothesis, but I'm trying to build and we are working on. But yeah, I think this is where we are. But I'll come back with more findings once we have more progress. Um, and this particular paper, Understanding Lomskagel Periodogram, was very helpful because there are a lot of nuances in applying Lomskagel, which I didn't quite find time to build the presentation. But like, how do you select the period, and like what is the how finely you slice the time is very important to find the right peaks in the frequency. So I think this can be a good read for any extension, or if anyone is interested to understand more on Lomskagel. Yeah, I think that's it on this presentation, but we can take up any questions if there is anything.
Okay, yeah, well done, Ashok. Very good timing too. You've kept very good to time. You went through a lot of material there very quickly, but what we can see now is that a Jupyter notebook in Anaconda with some very good graphical skills you have there. You can demonstrate the capabilities of Lomskagel compared to the original invention of Monsieur Fourier, who survived the French Revolution in one piece without losing his head. Very good. I mean, you know, I mean, I've never managed to do anything like that, but I'm now suitably motivated to actually use your framework to do a little bit of exploration of myself. So it works for me, and I expect it'll work for many other amateurs too, who might be saying, how would I ever get round that sort of stuff? Well, you have demonstrated that that can be done in double quick time too. I mean, this time last week it was, could you possibly do this? Now you've done it.
No worries.
Roger, how about that?
Yeah, I was just thinking what today has shown is there may be some interesting projects we can get involved in. One relates to non-eclipsing or even eclipsing binaries, looking at possible exoplanets around those. Another one might be analyzing TTVs to discover new planets. And the point of out of transit observations is they're useful not only for detecting stellar variability, but for looking for additional planets in the system. So
Yeah.
there may be some interesting projects come out of today.
Well, I think we might have made a start in the right direction with Ashok's quick fire demonstration of what can be done. You know, at first sight, Lomskagel seems very complex and probably not easily approachable by non-experts, but Ashok has managed to program that in a very well-known framework of Jupyter notebooks. You might not understand all the details of every line there, but they are actually approachable if you spend some time looking at his code. So really, really good. You got me enthusiastic. I suppose I should be anyway, shouldn't I? Right, so there we are. Roger, you've done your final piece this morning.
I have indeed.
So what we ought to do now is to see whether we can find some sort of wrap-up statements to make. the impression I have is that we've moved a step forward towards, despite the fact we couldn't listen to Pieter and his introduction of his exoplanet Pi, is that we are moving forward to the point where we can realistically expect to encourage and to capture amateurs, students, and real amateurs at home who don't necessarily be following an MSc, say, to actually motivate them to help them convince themselves that they could actually really do something significant. Not a huge discovery as such, although that might be possible too, but to actually make some contributions to professional exoplanet research. And actually, of course, we already know that our leaders in Exoclock are somewhat interested in the idea of extending the pro-am collaboration model that they've developed into other areas. And I would suggest that this is one of them.
Yeah, Rodney, I think the other thing is that with the amount of data now available from tests, etc., there's a huge field of data analysis that's opening up for amateurs, not just looking through telescopes.
Yeah, I think it's a point that can be now made quite forcefully, and what we've got to do is find some way to bring in additional people. Siegfried has written us a long commentary piece, so let's read this. Thank you, Siegfried. Yes, indeed. Of course, it's not going to be done by itself. We have to involve, as you say, radial velocity measurements and things like that. But these things can be developed. Obviously, radial velocity measurements are like hen's teeth, we say in English, difficult to get a hold of, difficult to convince observatories to focus in on. But if one can back up, if we can to some extent reduce the shortage of opportunities to do RV observations by powerful techniques developed by amateurs, that is one way in which to develop the field. I could read out the whole question, I guess. Perhaps I ought to do that. Yeah, okay, let me do that very quickly. So Siegfried says, basic problem with TTVs in one single observable exoplanet is that given the period of that exoplanet and the period of a TTV, determine the period of the possible perturber without doing RV observations. That's never going to be that easy. This problem is hard because the solution is not necessarily unique. Yes, we're going to get degeneracy, and involves comparing several possible mean motion resonances. Yeah, absolutely. So, but with additional experience and refinement of our techniques, maybe this informative amateur community can do just that. You say without RV observations, clearly with observations, with RV observations would be a significant improvement. Okay. Roger.
Yeah, I think it's been extremely useful. For those who are interested, I've had a exchange emails with Peter, and he's going to try and set up a video call with you, Rodney. I copied you on the email, so for you and your students, well, hopefully he can go through his presentation.
Okay, yes, we would like
He's
that
also
a lot.
going to send me a PDF of his talk, so at least we've got that. But he's not 100% by any means as yet, so it might be a
All right, well, that's another good positive outcome. Thank you.
Yes, despite the frantic Friday, we got through the day.
Okay. I think that may be a natural end then.
Yep. Thanks again to everybody who took part, who gave the talks, Callum, you, Rodney, and the speakers. So great day.
Okay. All right, folks. Well, we'll leave it there. Obviously, we were severely challenged by completely different timing, but we managed to do that, and everybody's had a good go at their presentations. And we look forward to reporting on further progress along several different approaches that we can take. So
Yep.
big, and thank you very much for Ashok and Daniel for coming in at fairly short notice to produce some interesting additional material.
No problem. Cheers.
And we want a copy of your, oh, well, we can get a copy of your Jupyter notebook. That would be really fun to read through.
Yeah, definitely, Rodney. I'll
Yeah,
share the
yeah.
GitHub link, updated one. What's the right forum to share, Rodney?
Oh, we'll find a way. We'll circulate it to the students who are interested in your work and make sure they take full advantage. If others want to use it as well, other members of the audience, just let us know. Let Roger know, and we'll pass it on. But Ashok's skill with changing parameters in a Jupyter notebook, faultless. That would take me much longer than Ashok is obviously a full-time computer engineer with very, very quick reflexes. Okay, right, I'm going to close down then, and thank you for coming. Hope that was useful, and we hope to see you again another day.
Bye then, folks.
Thanks, everyone. Good day.
Thank you.